And for our final project, we decided to design and implement a digital multimeter.
Okay, the system requirements are, there are 4 modes. You can toggle, the user can toggle between voltages, resistance, calculated current, and measure current modes by pressing button 0. The user can measure DC voltage varying from 0 to 3.3 volts with 99% accuracy. The user can input 3 color bands to find the value of the standard 4-band resistor, which can vary from 1 ohm to 99 gigaohms. It can also calculate the theoretical current through a resistor and measure DC currents from 0 to 4.35 amps, and that was the extra, which we added on.
For a system block diagram, a lot of this is familiar. Time encounter using GPIO. We took out the reset. We didn't see a use for it since you could just load the program again if you wanted to use all 4 buttons. We have our 2 GPIOs for the LCD. Using the SPI again, but the difference this time is we're using the VISO. We're reading in data from the analog to digital converter from the digital. And we have this current sensor we bought online. And in order to measure both voltages and currents, we used the 16:1 analog mux, of which we only had to use 2 of the pins. And we used the GPIO to control the bit to the mux according to whether it's in voltage mode or current measure mode. And it says the correct bit to the mux to input the right signal.
As Oscar just mentioned in the block diagram, our hardware was a Nexus 2 board, LCD display, the Digilant PMOD analog to digital converter, and we had the current sensor and the analog mux.
For software, of course we had to have an ADC read function. The trick to that we learned was you had to do a fake write to get the clock started.
Another thing we did on software, implementing in software, was the GPIO mux control. So we had a GPIO which would send in either 0 or 1 to the mux in order to control if we wanted the pin 1, which would read the voltage from across any resistor, or the other one's voltage from the current sensor. So there.
Of course, we had to have algorithms to convert the data we were the 12-bit string we were receiving from the ADC into the appropriate voltage and current, and display on the LCD. The voltage one wasn't as bad. The current, we had to do some tricky stuff because there was a lot of possibilities. We had from 0 to 3.3 volts and tons and tons of resistor values, so we had to do some tricks to be able to get our resolution in.
We had to use the averaging function in order for the voltage to stabilize, because it would jump around from, like, let's say 3.22 or 3.33, and then we took 10 samples, and then we divided by 10 to average it, and it would stabilize the voltage. It's pretty good. And the resistor function, what that one does is you can input any color band from the 3 color bands, and it will tell you what the resistance is of that resistor. And
and like I said, we have an algorithm to actually calculate the current from the resistor you inputted and the voltage you're measuring. And of course, you always have the error. If your resistance is 0, you can't divide by 0. So if that happens, it gives the error message on the screen. For implementation and testing, basically our first challenge was to get in any sort of data from the ADC, and we didn't have the LCD at first, so we outputted our 12-bit string, and you could toggle between the top 4 and bottom 8 with buttons and on the LEDs, and we could see if we were actually receiving in data. Then when we got the LCD, we were able to visually inspect if we were getting the correct numbers from our algorithms, and that's when we noticed that it varied a lot, so we had to implement the averaging function. From there, the current sensor and all the problems, everything's working.
We had some problems, obviously, when we were developing it. One of the problems we had was with the ADC to get the We couldn't get it to work first. It was mainly because we actually couldn't get the clock to work. And what you have to do is you have to use a fake write to the ADC, which is not really writing to the ADC, but it just pretends like it just to get the clock running. Another one of the problems was just like writing the code to figure out the right format to display the voltage in on the LCD, and because we had to convert it from binary to decimal, and then you had to use the percent mod function. And another one we had problems was with the current sensor, and with the color band resistors. We had to with the color band resistors, we had to.
The whole problem was getting we had to create a character array to get the right abbreviation for the colors and make sure they switched with the correct button. And at first we had it displaying an exponential, but we really wanted it to display like kilo ohms or mega ohms, and there's a lot of possibilities. So actually we got that working. One thing to note was one of our outstanding problems is with the current sensor, unfortunately, because it measures from 0 to 5 amps, and with the power supplies we could only go up to 1 amp, and that's a lot of amperage. So the accuracy is not that great. With more time, we probably could have implemented an op amp, which we tried to do, or ordered a current sensor that could handle a lot lower amperages with more resolution.
The way the current sensor works is at about it will output at 0 volt at a 2.5 amps. So what we had to do, what we would have done is use a summing op amp and put negative 2.5 on one of the pins on the inputs, and put a 2.5 on the other one. And as soon as a negative 2.5 and positive 2, and make it 0 to bring down the shift.
So we're ready to demo.